Hello, students. It's Mr. Rich. It is time for another math Q&A. I don't see very many people here at all. So what I'm going to do is I am going to be doing starting off with AP Calculus. So I'm going to share my screen, and most of my AP Calculus students are in Unit 3, which involves taking derivatives using the chain rule and also doing implicit differentiation, which is a version of the chain rule. So I'm going to do some work there, and then I'll probably switch over and do some algebra 2 to wrap things up. Well, let's go ahead and get started. So the first thing that I wanted to do is do a little bit of chain rule in section 3, lesson 3.2 of AP Calculus. And let me, first of all, let's go ahead and define what the chain rule is. So in calculus, what we do when we are taking derivatives of what we call compositions of functions, when we have a function that is a function tucked inside of another function, what we call f of g of x, if I'm going to take the derivative of such a function, we'll call it d dx. We're going to take the derivative with respect to x. What we do is we're going to take the derivative of the outside part, which is to say we're going to take the derivative of the f. So that's going to be f prime, right? The derivative of f, while we leave the inside part alone. And then we're going to multiply that by the derivative of the inside portion. So that becomes g prime of x. Now, that just using that symbology there kind of confuses students until you actually see what this looks like when you're doing a problem. So let's do kind of a basic, simple chain rule problem that looks like the following. What I'm going to do is I'm going to take a function that would be 2x minus 4 raised to the 5th power. Now, in order for me to take that derivative using the rules of derivatives before we learned the chain rule, I would have had to expand that polynomial out all the way. I would have had to take 2x minus 4 and multiply it by itself 5 times. And as you can imagine, that would take a while. I could use Pascal's triangle and do binomial expansion and all of that, but we don't want to have to do that to take this derivative. So what we really have is we have a composition of functions. We can view this as this function right here as the inside part. That's our g of x. But then we have an outside part, which is this part right here that's being raised to the 5th power. So when we take this derivative, it's going to look like this if I apply this chain rule. What I have is I have this whole inside part that's being raised to the 5th power. So I'm going to use the power rule and bring that exponent 5 out to the front and leave the inside part alone and drop the exponent by 1. So it becomes 5 times 2x minus 4 to the 4th power. And again, that is just our power rule, one of the very first rules of derivatives that we learned. But then by the chain rule, so what I just did right there is this part. I just took the derivative of the outer part. But now I do need to multiply by the derivative of this inside part, and that derivative would be the number 2, right? Because the derivative of 2x minus 4 is just 2. And so that becomes our derivative. We'll simplify that by taking the 2 times the 5, 2x minus 4 to the 4th power. So that is our derivative right there. Now, it can obviously get more complicated than that, and that's what I wanted to show you tonight, some of the ways that we can take derivatives with the chain rule. Let's start off by looking here at this problem. So this is going to be starting off with as a quotient rule problem because I've got a function on the top divided by a function on the bottom. But when I do get to taking the derivative of the bottom part, I am going to be using the chain rule. So let's rewrite this as follows. Let's do x over x squared plus 1 raised to the 1/2 power. So we're going to change our radical to a 1/2 power. Then when we take the derivative, we're going to start off by using the quotient rule. So when we do the quotient rule, we're going to take the bottom portion, right, the bottom, so the low, which would be x squared plus 1 to the 1/2, times the derivative of the top part, and the derivative of x is 1. Then we do a minus times the top part, x, and then times the derivative of the bottom. Well, the derivative of the bottom requires us to use the chain rule. I'm going to take the 1/2 and bring that to the front, leave the inside part alone, x squared plus 1, and then reduce that exponent by 1. But then I need to multiply by the derivative of the inside part, 2x. The derivative of x squared plus 1 being 2x. And then in the bottom, we are going to go ahead and take the square of the bottom. So when I square the square root, they will negate one another and just leave me with x squared plus 1. So I'm not showing you here the formula for the quotient rule. I'm just doing it, and I assume at this point that you understand how to employ the quotient rule, and that's what I did right here. This can be simplified for sure, especially this part. So when you analyze what I did over here, this entire part right here is the derivative of x squared plus 1 to the 1/2 when I took the derivative of the bottom part of our function. And that whole thing is the chain rule applied to x squared plus 1 raised to the 1/2 power. Well, if I were to simplify it, we'll just leave this as x squared plus 1 to the 1/2 power. And then over here, what's going to happen is my 1/2 times 2 will cancel. I will have x times x, so that's going to give me an x squared. And I have x squared plus 1 to the minus 1/2, and then that's all over x squared plus 1. Now, for sure, there is some more simplification that we can do here. I'm not going to go into the algebra involved in simplifying it further, except to say that I could factor out an x squared plus 1 to the negative 1/2. I could factor that out as a GCF. Not going to do that, although it is something that we could do to further simplify it. All right, so that is the chain rule. Let's try one more chain rule, and I'm going to do kind of a nested chain rule problem. I'm going to start with this one right here. So here I'm taking the derivative of the tangent of the natural log of x. So when we take this derivative, we are taking the tangent of a thing. That thing happens to be the natural log of x. But at this point on the outside part, I don't really care what the inside part is because I'm going to leave it alone. The derivative of the tangent of something would be secant squared of that something. So it's going to be secant squared times the ln of x, right? So because we know I'm using the derivative of tangent, which is secant squared, but I leave the inside part alone. But now I have to multiply that by the derivative of the natural log of x, which is 1 over x. And so this becomes our derivative right here. We could write that as the secant squared of the natural log of x all over x. Okay. Now let's go and do maybe a few more. All right, so here we've got the sine of cosine of 3x squared. Let's take this derivative. dy dx. It's going to be equal to. Well, what I'm going to do at this point is I'm going to say, well, what is the derivative of sine? The derivative of sine is cosine. So it's going to be cosine of cosine 3x squared. But then I have to multiply that. So this is the derivative of the outer. Derivative of sine is cosine. But I have to multiply now by the derivative of the inside part, and that is this. So what is the derivative of cosine? It is negative sine of that same quantity, 3x squared. But then I have to multiply by the derivative of the inside part of this, which gives me 6x. So that now becomes the final answer. I'll clean it up just a bit by bringing the 6x to the front, a negative 6x, because we do have a minus right here. So we'll call that minus 6x. And that's multiplied by cosine of cosine 3x squared. And then times sine of 3x squared. All right, so we used the chain rule 2 times in one problem there because I had this serving as an inside part to the sine, but then when I got to taking the derivative of this inside part, it had its own inside part, 3x squared, which generated the 6x multiplier out here. All right, that is enough of chain rule. I want to go and take a look at implicit differentiation, which would be section 3.3, lesson 3.3 in AP Calc. And what we're doing here is we're taking functions that are what we call implicitly defined functions. Functions that have y isolated on one side are called explicit functions because we have them defined explicitly in terms of just x. But when we have x's and y's mixed together in the function, then they're what we call implicit functions. And we don't want to have to bother solving this for y and then taking a derivative to find dy dx. We want to just be able to take the derivative of the function as it's presented to us. And so we're going to do an operation on both sides of the equation. We're going to take the derivative with respect to x on both sides. But let me explain what we're going to do when it comes to taking the derivative of y. So let me just talk just a little bit about taking the derivative of functions of x. So when we take a derivative of x to the third power, and we come along and we're going to take the derivative, we don't use the chain rule, right? Because we are taking it just, it's just x to the third. So we just call it 3x squared. Easy enough. But really, you know, I tell my students this all the time, that we're really doing the chain rule all the time. Because if you think about this as being the derivative of x inside parentheses to the third power, what I'm going to do with the chain rule is I'm going to take the 3 times the thing on the inside, which is x, reduce the exponent by 1, and then I'll multiply by the derivative of the inside part. Well, the derivative of x is just 1. Okay, so it does end up being just 3x squared. So when the function that we're working with on the inside is just x and nothing else, then we really don't use the chain rule because the derivative of x is 1. But once this becomes something other than x, that's raised to the third power, like, for example, let's say that it is sine of x to the third power. So I'm going to take the derivative of sine of x to the third power. Well, I'm still going to use the power rule. And it's going to be, when I take the derivative, it will be 3 times the thing that's inside, sine x, but now to the second power. But then I'm going to, by the chain rule, take the derivative of that inside part, which is cosine, and I multiply it by cosine x. Notice that the multiplier up here was a 1 because the derivative of x is 1, but here the multiplier is cosine x because it was sine x. But that takes me to, what if it's y to the third power and I'm taking the derivative with respect to x? What if it was the thing on the inside was y and I want to take the derivative? Well, it would be 3 times the inside part that we leave alone to the second. So I treat it just like it was an x. 3y squared. But I need to multiply by the derivative of y, and the derivative of y is dy dx. So every time we take the derivative of the y variable in these equations that we're about to work, then we're going to tack on by the chain rule a multiplier of dy dx. That's how we handle derivatives of y that are mixed into our function along with the x's. We treat it just like it was an x variable, except for the fact that by the chain rule, we have to add a multiplier of dy dx. That being said, let me show you then what this problem would look like. The first step is to take the derivative on both sides of the equation with respect to x. That's the operation that we're doing on both sides. The derivative of 8x squared, easy, 16x. The derivative of y squared, though, would be 2y times dy dx. And then the derivative of 10 would be 0, because when we take the derivative of a constant, as you know by now, that answer is 0. And then what we do is we're going to solve this for dy dx. So I will move the 16x to the other side. So we'll leave this as 2y dy dx here on the left. That comes over as a negative 16x. And then we're just going to divide both sides by 2y, right? We're just using our algebra skills at this point to isolate the dy dx. We divide both sides by 2y, and then we are left with dy dx as a final answer, simplified, negative 8x over y. And so our derivative is not just a function of x, it is a function of both x and y. All right, I'm going to do a few more of these, and I'm going to do one that involves finding an equation of a tangent line, because I'm going to use Desmos and show you that it's legit, right? That this thing actually does work. We're going to do this problem here, number 9. This says to find the equation of the tangent line and the equation of the normal line to the curve at the indicated point. Well, to find equations of tangent lines, you know that we're going to be using our point slope form. Y minus y1 equals m times x minus x1. Well, the point of tangency was already given to us, 2, 3. So that's what's going in for x1 and y1. But what we need is we need to know what the slope is. So we're going to have to find dy dx at the point 2, 3. So that is what we're going to go do right now. So we'll take the derivative on both sides with respect to x. This becomes 3x squared. When we take the derivative of this is a product rule. So I have to be ready to use whatever rule pops up. And this is two functions being multiplied. Therefore, I have to use the product rule. So I take the derivative of the first function, the derivative of 2x is 2, times the second, which is y, plus the first function 2x times the derivative of the second. Well, the derivative of y would be 1 times dy dx. So this becomes 2x dy dx. Then I move to the next term, and this would be negative 2y. But again, I got to add a dy dx multiplier by the chain rule. And then that would be equal to 0. Because remember, what we're doing here is we are taking the derivative on both sides of this equation with respect to x, and the derivative of a constant will be 0. Now, instead of doing the algebra on the dy dx here, I'm going to just take the points or the point 2, 3 and put in its values into the equation and then do the algebra to solve for dy dx. So this is going to become 12, right? 2 squared is 4 times 3 is 12. 2 times y is 3, right? So we're putting a 3 in here, so that becomes a 6. 2 times x, x is 2, so that becomes 4 dy dx. And then over here, minus 2 times y, that would be minus 6 dy dx. And that is equal to 0. Next, I'll combine like terms. I've got an 18 right here that I'm going to push to the other side and make that a negative 18. These two terms give me a negative 2 dy dx. And then I would be dividing both sides by negative 2 to get dy dx is equal to a positive 9. All right, that allows me to go ahead and write the equation of the tangent line because we've got the point of tangency here. So that means we would do y minus 3 equals 9 times x minus 2, like that. Now let's see if we did this right. There's lots of places here that we could have made a mistake, and by we I mean me, but let's give it a shot. We will clear all of this out. And let's go ahead and plot the actual function itself. This is not going to be a function, I don't believe, because it is, we'll take a look at what it looks like, equals 11. Yeah, so definitely not a function. You can, if we zoom out, let's see if we get a full picture here. Yeah, it looks like that's the whole thing right there. Well, let's go ahead and plot the point 2, 3 and see where that is. 2, 3. It's right there. So we'll zoom in on that. And that's where they wanted us to find. Now, I like that the slope is 9 because that looks like the tangent line is going to be extremely steep right there, almost vertical. But let's go ahead and put this equation in. Y minus 3 is equal to 9 times x minus 2. Yeah, it looks like we got it dead on. So you can see that that green line, which was what we thought was our tangent line equation, it does look like it's hitting the function right at that point, 2, 3. Okay, so I think we've got that. And then, one of the things that we know about these tangent lines is that when you zoom in, if you keep zooming in far enough, you cannot distinguish between the tangent line and the actual function itself. You can kind of see it down here as it separates, but when you're right there at the point of tangency, you really can't tell if the function looks almost linear and those two are laying on top of each other until you zoom out, and then you can see that, oh yeah, there is an underlying function and that tangent line is coming in and nicking the curve at that one point of tangency. All right, so at this point, a lot of students in calc wonder, like, why would we want to know the equation of a tangent line? And there's several reasons why we need to know equations of tangent lines. And we'll be showing that to you throughout Unit 3 and Unit 4. But for now, we just want to be able to come up with the tangent line equations by finding the slope at a particular ordered pair. Well, let's go ahead and move that back. And I think what we'll do now, it's about 8:30, so let me see if any questions did come in to my email from my students. While I'm doing this, I will mention to you that we do have an SAT group that just started for the November 8th SAT. And if you are interested in joining, you still can join. It meets most Thursday nights. We had our first session this past Thursday, but if you are interested in joining, you still could do it, and because we record each session, and you can see there on the screen for the November 8th test. What you get for this group prep is you do get a full set of third-party practice materials that are outstanding. It's called College Panda is what we use. And you also get access to my online classroom with extra videos and lessons there. We do 6 live small group sessions, and those are 1 hour, one per week leading up to the test on November 8th. And would love to have you join us. And you can visit or you can email me there at my email address if you're interested in joining. Okay, great. So let's jump over. I'm going to do a little bit of work in Algebra 2. And what I want to talk about is quadratic equations. Most of my Algebra 2 students are getting into quadratics this time of year. And also, if you're an SAT student, if you're prepping for the SAT, you know that quadratic functions are a significant portion of the SAT in the algebra and advanced math sections. So you really do need to know quadratics inside and out. And Algebra 2 really is where we try to teach you everything that you need for your SAT. But let me just remind you of a few things about quadratics that are going to help you. We start with the fact that quadratics are often written in what we call standard form, ax squared plus bx plus c. And what we know about quadratics that are written like this, and I'll give you an example of one, right? Y equals x squared minus 7x minus 18, where a would be 1, b would be negative 7, c would be minus 18. Well, what do we know about the graph of the quadratic based on the equation written in standard form? Well, there's several things that we do know. We know that because the a is greater than 0, being that it's a positive number, that it's going to be opening upward. The a value being a negative would cause it to be opening downward, right? This is going to be the shape of a parabola. We know that. Quadratics take that characteristic parabola shape. But because a is greater than 0, it's opening upward. We also know that the c is going to be the y-intercept. So we do know the y-intercept from the equation, because that last term, the constant term, when x is 0, the y will be equal to that term. So therefore, the y-intercept is going to be at the c value for us, right? At negative 18. And let's write it just generally. It's 0 comma c would be our y-intercept. We also know something called the axis of symmetry. When a quadratic is written in standard form, there's a formula that you need to know for the axis of symmetry. X equals negative b divided by 2 times a. So that would be the equation of the vertical line that's going to pass right through the middle of the parabola and therefore go right through the vertex. And that's how you could calculate that x coordinate of the vertex right there. And then if you want to know the y coordinate of the vertex, you could plug that value back in. All right, so that is one way that we write equations. Now, in Algebra 2, you're going to learn that there's a second way that we write quadratics, and that is when they look like this in what we call vertex form. X minus h squared plus k. So again, there are 3 constants, a, h, and k, and it's not a coincidence that we're leaving this as the letter a, because whatever a is when the quadratic is written in standard form, it's going to be the same value that I would put in front of the parentheses here in vertex form. Now, what do these represent? Well, when the equation is written in vertex form, h comma k is going to be the coordinates of the vertex of the parabola. That's going to be the minimum or the maximum value. That's what we know. And of course, a being positive means it's going to be opening upward. If it is positive, if it's negative, it would be opening downward. But that is primarily what we know when the equation is written in vertex form. The third form that we could write a quadratic in is in what we call factored form, or some call it the x-intercept form, but I will call it the factored form. And what this is going to look like is this when we write it as y equals a times x minus x1 and x minus x2. And what are the x1 and x2? Those would be the x-intercepts. x1 and x2 are the x-intercepts for the parabola, like that. So those are the 3 ways that we do write equations of parabolas or quadratic equations. So now if we take this one that I just came up with right here, and we wanted to write it into its factored form, we could try to factor that quadratic. And you learned back in Algebra 1 how to factor those quadratics. So let's come down here and let's write that. See if we can factor it. Well, I'm going to factor it as the product of two binomials. Now my a is a 1, so there's going to be just a 1 in front of these two factors. Well, I'm looking for two numbers that would multiply to be negative 18, but add to be negative 7. And that would be a negative 9 and a positive 2. So that is the factored form of that quadratic. And that tells you that it is going to pass through the x-axis at 9 and negative 2. All right. Now, so that's the second way that I could write that parabola. Now, could I write that parabola in its vertex form? Definitely, yes, I can. Now, there's two ways that I could write it equivalently in its vertex form. One is a method that your teacher will probably teach you called completing the square. I'm not going to show that to you here, but I'm going to just show you how I will find the x and y coordinates of the vertex so that I could put them in for h and k. So what I'm going to do here is I'm going to use that formula right here for the x coordinate of the vertex. So coming over here, the x coordinate will be negative 7, which would be a positive 7, divided by 2, which we'll just call it 7/2, 3.5. Now what I'm going to do is I'm going to plug that into the function for x and see what the y coordinate is. So that would be 7/2 squared minus 7 times 7/2. Let's rewrite that. 7 times 7/2, and then minus 18. All right, so let's see what this is equal to. So this would be 49/4 minus 49/2 minus 18. So let's get a common denominator here of 4. This would make this 98/4, multiplying top and bottom by 2. And this would be 72/4, right? I would multiply this top and bottom by 4. So that gives me negative 72/2. So let's see what this would be. So if we do 49/4 minus 98/4, that's negative 49. And then I take 72 away from that. So if we add 49 and 72, looks like we get 121/4. So that would be negative 121/4. That would be the y coordinate of my vertex. So that means the vertex would be 7/2 and negative 121/4. Like that. That means I could plug that into the equation and it would look like this. It would be y is equal to, my a is 1. So we'll say though x minus 7/2 squared minus 121/4. That. And that would be the equivalent form. Now let's go over to Desmos and let's just see what happens if we were to graph these. Let's see if this is legit, that these are the same parabolas in 3 different forms. So we'll do the y equals x squared minus 7x minus 18. And zoom out a bit. There we go. All right, let's try the factored form. Y equals x minus 9, x plus 2. Okay, and you can see that those two overlay perfectly. Now, the next one, since fractions were involved, kind of have my doubts on this one, but let's try it and see. So y equals, coming over here, this was our equation right here in vertex form. Let's see if this really works. Y equals x minus 7/2 squared, and then minus 121/4 fourths. Yes, it does work. So you can see that although that is kind of an ugly form of the equation with those two fractions there, it does indeed overlay perfectly on top of the other functions there. So if we turn the purple one on and turn the red off, we can see. So those are all three equations representing the very same parabola. So now, what are some of the things that that you need to be able to do in Algebra 2? Well, we do have to be able to convert between these between standard form, maybe, and vertex form. So let's work a few examples. Notice in these problems here, it says write each function in vertex form. Now, I am going to write it in vertex form. I'm going to use the method of finding the coordinates of the vertex. Okay, so I'm going to use the fact that it's negative b over 2 times a, which would be 8 over 2 times 1. So the x coordinate for the vertex would be 4. That's our axis of symmetry, x equals 4. Now we'll plug the 4 back in. So that would become 4 squared minus 8 times 4 plus 18. 16 minus 32 is negative 16 plus 18 is 2. So it looks like we've got 4, 2 as our vertex. The a is a 1, right? We can see that there. So when we rewrite this in its vertex form, it's going to look like this. It's going to be x minus 4. All right, remember, even though my x coordinate is a positive 4, it is going to be x minus 4 squared and then plus 2. And that will be the same graph as this one, just written in vertex form. Now, could this be factored? Are there two numbers that multiply to be positive 18 and add to be negative 8? Doesn't look like it. So it would not be an easy thing to write it in its factored form. Okay. Now, I do want to wrap this up, I think, by showing you something called completing the square, which would be a way to do this. And I think your teachers, most of your teachers, want you to be able to demonstrate that you know how to do completing the square to get this into that form. So I want to show you that method right here. And let's try it. So here is the method. I'm just going to show you the method by working this particular problem. Here's what we're going to do. I'm going to take x squared minus 8x and move the plus 18 over just a tad to give me some space to put another term in right here. Now, what term am I going to put there? I'm going to put a number there so that this trinomial, that would be right here, so that those three terms would be what we would call a perfect square binomial. Now, how do I pick what that number is going to be? Well, it's pretty easy. I'm going to take this middle coefficient, the negative 8, in front of the x, and I'm going to divide it by 2, and I'm going to square it. Well, negative 8 divided by 2 is negative 4. And then when I square that, I get a plus 16. Now, as you well know, I can't just arbitrarily stick a number in there, plus 16. I have to offset it by putting a minus 16 on the same side because I need to keep the equation the same. But now what I can do is I can factor this, right? That is going to be x minus 4 times x minus 4, this right here. But I'm not going to write it like that. I'm going to write it as x minus 4 to the second power. 18 minus 16 is a positive 2. And that is my completing the square. So you can see I get the same exact answer that I got right there. That's completing the square. I'm going to show you one more problem where I'm going to complete the square. We'll do it on this one here. Now, before I complete the square on this, what I'm going to do is I am going to factor out the -1. And I'll put a negative out here. So when I factor the negative out, it does put x squared plus 6x. And what we'll do is we'll put this here, but we'll leave this -5 out here. So the minus is going to change the sign, and this is going to be a -6x right here because I'm pulling a negative common factor out, which will change that to a positive x squared, and it'll change that to a -6x. This doesn't get changed because I'm leaving it set out here. All right, so I am going to take half of -6, which would be -3, cut that in half, and then square it. And that's going to give me a +9, like that. Now, what do I have to put out here to offset that? Well, by putting that +9 right there, that minus that's sitting out here would be distributed to that 9, making it a -9. So I'll offset that by putting a +9 right here. So what does this look like? F of x is going to be equal to a negative, and I will factor this to be x minus 3 to the second power, and then +4 when I combine those two terms together. So that tells me that the vertex is going to be at 3, 3, 4, like that. And that's that. And there's my vertex. And it's written in its vertex form right there. All right. If you've got any, we do have a few viewers here. If you've got any questions, be sure to post them in the comment section. I've got 15 minutes left. If I don't have any questions, I'm going to check to see if any of my students did submit a question. We're going to knock off things a little bit early tonight, it looks like. I will do one other thing I wanted to show you was I wanted to remind students how to factor trinomials. Checking for any questions. It does not look like it. All right, so here's going to be my last thing to show you tonight. I want to remind you of a way to factor quadratics that have a leading coefficient other than 1. And I'm going to show you a method called the AC method. And here is the AC method. I'm going to multiply the A and the C of the quadratic. 5 times 12 is 60. And then what I'm going to do is I'm going to ask myself what two numbers multiply to be 60, but yet they add to be a +19, that middle term right there. Well, if you go through all the ways you can multiply to get 60, two numbers to get 60, one of the ways would be 15 times 4. So the answer to that riddle is 15 and 4. The sum of 15 and 4 is 19. The product of 15 and 4 is 60. So now that I've identified those two numbers, what I'm going to do is replace that middle term, 19n, with those two terms, using the smallest one first, plus 4n, plus 15n, and then plus 12. So I haven't really changed the function at all. I've just simply replaced the 19n with two terms that do combine to be the 19n. Now, why does that help me? Well, what I can do is I can do something called factoring by grouping. I can split these four terms into two pairs and then factor out the GCF from each pair. The GCF on this first pair is just an n. So I pull that out, leaving me 5n plus 4. This pair of terms has a GCF, it looks like, of 3. So I will pull out a +3, leaving me 5n plus 4. What happens when you do factoring by grouping like this is you'll notice that I have a common 5n plus 4 between these two larger terms. So I pull that out as its own common factor. And when I pull that out, what does it leave? another factor of n plus 3. Okay, so that is what we call the AC method of factoring. Now, the fact of the matter is this, that when you are working in higher level math, and I would say this includes your AP Pre-Calc and your AP Calc, if you do encounter quadratics that have a leading coefficient other than 1, you really don't even need to use the AC method. What you want to use is a trial and error method. In other words, if this first term can only be factored one way, like 2n and n, that is the only way that you're going to split up that 2n squared, then I've got only a couple of options. 2 and 1, right? In other words, 2 times 1 is what gives me 2. This term comes from the product of the last two numbers. So this is either a plus 1 and a plus 2, or it's a plus 2 and a plus 1. So if we try plus 1 plus 2, I know that this is the right factorization, because obviously the 2n and n give me the 2n squared, and the 1 times 2 gives me the 2. But the middle term, 5n, is a combination of the outer product and the inner product. So what I do is I look at the outer as 4n, the inner is 1n, and they combine to be 5n. I know that I factored it correctly. So when you look at problems like this, like that would not be a good one for trial and error, because there is more than one way that you could factor the 9k squared. It could be 9k and k, or 3k and 3k. Don't want to do trial and error there. I would probably go ahead and do an AC method. I'll show you another one that might be a good trial and error. This one would definitely, right? So this would be 2v and v. And the product is 5. So this is, let's try 5 and 1. Let's just stick that right there. Now, does that work? My outer product is 2v. My inner product is 5v. That gives me 7v. Not enough. So that doesn't work. So what I'm going to do is I'm going to flip it around and put this as plus 5 and this one as plus 1. When you check your outer and inner products, the outer product is 10v. Inner product here, 1 times v is 1v. That does combine to give me 11v. And so I have the right factorization. All right, students, that does it all for this week of Mr. Rich Q&A. I will be back again next week, October 12th. So come by. Let me know if you have any questions. If you're one of my students that you're watching this either live or you're watching the recorded version of it, send me your questions in advance. You've got my email address. I'd be happy to work your homework questions here and give you a bit of a hand. Okay. So I hope everybody has a great week. We've got one more week left in the quarter here in our school districts in this area. So hard to believe we're about 1/4 of the way through the school year already at the end of this coming week. If you've got tests coming up this week, I wish you all the best of luck, and I will see you next week. Bye, everybody.